right, welcome back to Computer Science E259. This is lecture 10, XML Schema continued. So tonight we will finish our look at Schema and focus on some of the neater, more powerful features of this language. And again, to be clear, actually, let me not be clear and let you be clear. What's Schema good for? What's the point of all this, perhaps?
Definition.
Definition?
XML language.
Definition of XML language. Okay, so writing a spec for the format in which you want to exchange data, you want to present data to the world and such. We'll see when we look at XML web services in the weeks to come that these things are useful in that context as well, if one is looking underneath the hood at exactly how the data is going across the wire, so that you know what to expect if writing the processor at either end. So last time, recall, we did look at Schema. We looked also a bit at Project 4. Let's look at those in reverse then. So Project 4 has you implementing, at least this week and last, the left-hand side of this picture, or perhaps not last week, but this week for many of you, which is still fine. So we gave you the framework with which to implement this faux e-commerce system. One of whose implementation details is a catalog servlet whose purpose in life is to display the content in a large XML file of warehouse information. Also a cart servlet, which handles the more interesting part of actually checking a user out and allowing them to add items to their shopping cart and such. Well, to where do they check out? Well, that purchase order, as you'll see, will be submitted to a web service, which we'll round out our discussion of next week when we talk about a toolkit from Apache called Access, with which you can generate what's called skeleton or stub code, which means that based only on an XML description of some service, like a purchasing service, like a stock ticker service, like a news service, can you actually generate with tools like Access Java code or code in other languages that allows you to write RPC-based calls to that remote service. And it's actually pretty cool how this can be automatically generated. And in fact, in Project 4, recall the 100-some-odd files that we've given you in the com directory in our source tree was generated automatically based on Amazon's own XML WSDL file, as it's called. So there was a heck of a lot of stuff last time, which were mostly, this list I suppose is mostly a list of jargon, and we'll tease apart now today some of the more interesting features that were particularly lacking from the world of DTD, with which we simply couldn't express certain capabilities. And so we'll continue our discussion along those lines. So recall that there are a whole bunch of data types within the world of Schema. Here's a hierarchy, which is useful if only as reference so that you know that it exists. But for the most part, if you can think of it, they put it into the list, including with such specificity as positive integer, non-negative integer, unsigned long, and so forth. There's a great number of them there, some 40-odd data types possible. So we talked last time, too, about defining elements. And here is actually excerpted from the Schema number 1 recommendation, the canonical definition of an element. So notice that there's actually a whole bunch more attributes than we've looked at per se. All of these can be looked at either in the recommendation, but more reasonably in, say, the W3 Schools reference is a good place to start. Today's handouts are meant to be a quick reference guide to some of the things you can do with these things, but for the most part, I think we'll continue today to look at Schema by way of example, which is a bit more self-explanatory, I think, than some of the grammar, for instance, that you'd see in the spec. Attributes, too, have some additional details than those we looked at last time. Prohibited, for instance, is another type of use that we didn't even look at last time, and then there's some additional fields which we indeed did. So last time we concluded on a note with a promise that in this world of Schema there are simple types and complex types. And in this world of complex types, there are simple content, there is complex content, and a couple of other things, which makes it entirely confusing on first glance, perhaps. Well, let's start with the easier one. So last time we said that something is of simple type under what circumstances?
Has no elements.
So what do you mean has no elements?
It has no child elements other than their text.
Okay, so has no child elements, child elements, and it may or may not have attributes, yay or nay?
May have attributes.
Okay, and so may have attributes, and attributes in turn are of what type? Or can they have attributes? So remember that attributes were by nature of simple type, because we did conclude that attributes cannot have other attributes and clearly can't have children. So if we sort of reason backwards from that, simple types are simply things like strings. Like in this case here, a last name field, an age field. One might be a string, one might be defined as an int, but no such attributes. As soon as you introduce that, you introduce, we'll call it complexity. Okay, and we'll tease apart that latter part here. So attributes, though, just to be clear, are themselves are of simple type. Takeaway here, we have the canonical declaration up top, and again, this should be old hat, most of this stuff from last week. If we had an instance of an element like student whose gender is male, whose name is John Harvard, presumably there, well, how would you go about declaring that particular attribute inside your schema? Well, we saw such things as this last time, where gender is going to be a string, and we waved our hands at the additional details. But today, we'll focus more on restrictions and these things called facets, so that you can actually specify that gender can only be male or female or M or F, and those kinds of that kind of specificity. Fixed values. So we looked, I think, at maybe one instance of this by way of example, but with this fixed attribute, recall that you can actually require that if an attribute is indeed present, it must be that particular value, and if it's not present, it will be assigned. That is, it'll be auto-magically inserted so that you, the application receiving this parsed element, this parsed document, by way of, say, SAX events or a DOM, can trust that it will, in fact, be there. So it's a way of patching holes, potentially, in your data. But you can also have attributes that are optional or in fact, or simply required. So by default, attributes are optional. You simply don't specify what their use is. But by contrast, if you do specify required, the thing has to be there. And required is distinct from this notion of fixed in that it's got to be there, but you don't care so much what it is. But the first line there, where use is optional, that is unnecessary information to convey, because that's in fact the default. So they can be there, they can't be there. So here's where things get kind of neat and expressive with Schema. So this is actually a screenshot of the reference we keep pointing you toward, the W3 Schools tutorial on Schema, and these are an example of what's known as generally a facet. It's a means by which you can restrict what are otherwise simple data types. And again, a simple data type is like a string or an int. But if you care about what those strings look like, M or F, what those ints look like, maybe the number 0 through 9, well, you can specify that with these things called facets, a few of which, or all of which are listed there, a few of which we'll take a look at. So if you wanted to, for instance, define something known as a year, so this is going to be an element called year, what values are possible based on this definition of year, would you say? So a year is an int between... Sure, right? This is pretty easy. So 2007 and 2010, or if we want to be difficult, we can define it yet another way using Schema's additional expressiveness and just say between 2006 and 2011, but exclusive of those two values. So it just demonstrates two possible ways, and you can combine the two and come up with yet two more combos if you prefer. Restricting by value. So here, if we have the notion of, say, a major, like in a collegiate sense, and you ultimately decide the base type here is going to be a string. At the end of the day, your major is a string, but I only want it to be of one of three possible values. You can use the enumeration facet and specify that you're restricting strings to take on only one of three possible values. In this case, English, math, and physics. If instead you wanted to factor out that definition and reuse it, we'll recall from last time that you can define types as named types. They don't need to be the so-called anonymous or inline types. So here we're declaring major to be of type majors, which we arbitrarily define with the bottom statement there of simple type, but otherwise things are the same as before. And let's ask the who cares question here. Who cares? Why would you use a named type in this way as opposed to just version A of this thing?
You can use it over and over again without having to re-specify it.
Yeah, so you can reuse these things over and over again. So for the sake of code reusability, which for something like majors, maybe not be compelling in an example, but we did see a couple of examples last time, like names, I think, where we wanted, or comments, we wanted to reuse that notion, and it's just unnecessary, if not wasteful, to declare those things in two different contexts. What about patterns? So now we get more power, and we have this ability to express regular expressions, which is way more than we were able to do in DTD. So this top idea there, based on what you know of regular expressions, what values are possible for an element called choice?
A, B, C, or D.
Perfect. Not quite combination, but these square brackets that are around A, B, C, D mean that you have a choice of any of the symbols in between those two square brackets. So what this indeed means that a choice element, if declared in a document, its text child can only be lowercase a, or b, or c, or d. And it's the square brackets that imply as much. Well, what about this bottom example? Slightly different, but knowing, if you're familiar with regular expressions, what does initials mean?
First one's capital A through Z.
Mm-hmm.
Second one's capital A through Z. Third one's capital A through Z, but it's optional.
Perfect. So do you have either a 2-character initial or a 3-character initial, all in capital letters? So just to be clear, someone like me could have initials that are DM, that would adhere to that schema, or we could have the JM also adhering to that schema. So the question mark, as in most languages, just denotes 0 or 1 instance, aka optional, for that last bracketed set of characters. Okay, what about this? So just to give you a bit more syntax, also in the spirit of these regular expressions, you can also enumerate not just individual characters with those square brackets, you can also enumerate possible values. So in this case, gender, as you might hope, can either be male or female, the vertical bar denoting the OR operator there. And down here, we can get a little more interesting. What is a password? What does a password contain, according to this definition in English?
Can be lowercase a through Z, uppercase a through Z, or a numeral 0 through 9.
Okay. And then?
And it can be up to 8 times, can occur up to 8 times that.
Okay, and it must occur 8 times, in fact, given that syntax. So just to summarize even more precisely, it's a sequence of 8 alphanumeric characters. I'll summarize it as that. So this is weird syntax, but this does appear in a bunch of languages, Perl, PHP, and other language contexts that support regular expressions. Still bracket notation, which means you only have the choice of one such character, but these minus signs here allow you to specify a range of characters from A through Z to capital A through Z, and so forth. Okay, any questions? Oh, and the curly brace notation there means that we can actually, we have to actually pick 8 such choices each time around. So any questions on these facets, restricting by patterns thus far? No? Okay. Well, let's see, not bad so far. See if we can beat some of the ice home today. So restricting by pattern. Okay, so slightly more interesting, applying perhaps one of the principles we just applied. This here defines the product number type, so to speak, as a string ultimately, but someone else this time. What's this one equal? What is a product number defined to be? Again, even if you've not seen these kinds of things before, take a guess.
It's 3 digits dash 2 capital letters or 7 digits.
Perfect. So rather an arbitrary example perhaps, but yes. So it's 3 decimal digits, so 0 through 9, followed by 0 through 9, followed by 0 through 9, followed by a literal hyphen, followed by 2 uppercase letters, or the thing is just 7 digits long. And that's the difference implied there. All right, so just to generalize and toss the jargon there, lest you be looking it up in some resource that uses these things, this, generally speaking, is a regular expression. And for many of you, this is presumably old hat, but just to put some specifics here, anytime you're using the OR operator, it's conceptually like a branch. It can either be this thing or this thing. And if it's in either of these, what we describe these little pieces as are so-called atoms. So this is an atom because it denotes some symbol. This is an atom here because it is some symbol. Same deal here. This whole sequence represents one possible symbol. And now these things in curly braces are quantifiers. And they denote, as we've seen, the number of times that you want to do something with the preceding atom, which this here too is then an atom with a quantifier right next to it. So that's sort of the general syntax. And again, if unfamiliar, if familiar, know that Schema just stole the idea of regular expressions from a lot of existing languages. So useful things to know. is what these things can represent, atoms and so forth. This is really just a formalization of the things we've looked at thus far, but some curious ones to note, or to tuck them away if you've never seen them. \d is just a digit, like we've discussed, 0 through 9. If you want to invert that notion, \D means anything but a digit, which can be useful to express. \S is for any type of white space, \n, a new line, which you've seen, I'm sure, and \question for a question mark, because remember that a question mark is a quantifier that says 0 or 1. So you have to bear that in mind if you want to express it. And then finally, to summarize, these are the possible quantifiers, and we've not seen examples of all of these, but it turns out that not only can you say, give me 8 of these things, you can also specify a range. This means give me at least n of these things, and this means give me at least n, but no more than m of the preceding things. So that too can be useful in some contexts. Oh, and the plus, just to be clear, for those who've not seen these before, what does a plus mean as a quantifier as opposed to a star? 1 or more. So if we have something like \d star, that can mean 0 or more numbers. This, by contrast, means 1 or more numbers. So that, therefore, is equivalent to \d star is the definition for what plus means. Okay, any questions? So yes, I believe so. So I did not include it here for some reason, but yes, that should be totally fine to actually flip which values where. So you say, I don't care about the minimum number, but I do care about the maximum number. So yep. All right, so white space. This was a popular theme a while back as to how you can accomplish certain details with white space. So let's take a quick look at these. Also drawing upon some facets, but a different facet, the white space facet. And notice the annoying capitalization, but do take note of it. So a name, in this case, is ultimately going to be a string. And when it comes to any white space inside of that name element, preserve all of it, is the implication of this facet, as opposed to assuming that things may just be pretty printed, and therefore you should strip away leading and trailing white space inside the name element. This says, go ahead and preserve it, which recall is the default behavior for a document you're validating, which is the default for a document that has no DTD specifying it. It is all preserved by default. A name in this case means to replace the white space. So what does that actually mean? So in this case, and this is in the interest of normalization, it will take all white space characters, like tabs and form feeds and new line characters, and replace them with just single spaces, so that you just get one long line of text conceptually. By contrast, if you actually want what's typically considered normalization, you can also collapse white space. So yes, this thing is a string, this thing called name, but its white space should be collapsed. And by that, it means if you have 2 or more instances of contiguous white space, like 10 white space characters or a few new lines followed by tabs, collapse all of those contiguous spaces into just one single space. The motivation being you at least haven't thrown away all space, but at least you have some separation from what might be to the left and what might be to the right in the document. So that too there is useful in context. Well, what about length? So besides using regular expressions, if you don't really want to get into the details of specifying what these strings look like, but rather their length at least, you can also restrict by length, specifying this thing's a string, but the password must be of length 8. Or you can specify min and max and specify, similar in spirit to the quantifier notation in the context of a regular expression, that the min length of a password is 5 and the max inclusive is 8. So yet another way of approaching that problem without regular expressions. So this is kind of a weird thing that we've mentioned a couple of times, probably not all that common. I've always found this to be a bit of a not terribly elegant approach to having list data, but you can indeed, as with DTD, have lists of pieces of data. NM tokens, for instance, was an example of that in DTD. So if you've got an instance of XML like this up here, the means by which you could express the allowance of that kind of string of data is that you can say that grades, at the end of the day, are just a non-negative integer. They are just non-negative integers, but a list thereof.
And a list is demarked by one or more instances of white space in between all of the values. So all this is saying, if you define grades with this schema here, is that every grade is a non-negative int, and you just got to separate different ints from each other with some amount of white space. But that otherwise will be parsed one after the other, checked whether it's an int by the schema processor, and if so, you're good to go. Otherwise, it's invalid. Okay, unions allow you to do something that's maybe not worth dwelling on too much, but they allow you to express different possible types. And this is the last of our examples of simple types here. So notice at the top we have this example of a jeans size. And that can either be a size by number or size by string. Maybe this is reasonable in some contexts where you need a bit of flexibility for whatever internal reasons. That a jeans size can be expressed either by number or, again, by some string, like small, medium, large. Well, we might have a simple type called size by number here. At the end of the day, it's a positive int, but the maximum value possible for that is 42. Don't really care about the lower bound. If, by contrast, we care about small, medium, and large as allowed sizes, we can define that here. So all this schema up here is saying is that a jeans size can either be some number less than or equal to 42, or it's quote-unquote small, medium, or large. So it's just a way of saying that either of those is possible. And thus ends our look at simple type. So despite their simplicity, there's actually a lot you can do with them. But frankly, I do think it's fairly straightforward, or certainly self-teaching at a point, especially if you consider like a table like this, and especially look at a reference like W3 Schools, where if you want to dive in deeper about any of these things, you can just click on its word and on the link and get more information about it. So they're all, sometimes the verboseness can be advantageous when figuring out what's possible. Any questions on schema and simple types? No? All right, so now we get to complex types that can be simple, element, mixed, or empty. So this is always a weird thing, jargon-wise, to say that complex types are simple, but let's take a look. So if you have something that's of complex type, that allows you to have 4 different content models. And we talked about content models in the form of DTDs when we said you can have element content, you can have mixed content when you have PC data and or element content. Well, for now, an element is of type complex, and it has a simple content model if it's only children or text. That is, there's no complex hierarchy beneath the node. It's pretty darn simple. It's just something like, quote unquote, Jerry Seinfeld. But the upside of it being complex is what? What do you get as soon as you declare something using the complex type notation as opposed to a simple type? Still can't have children with this content model, but what can you have? Coming full circle to our query at the start of the lecture. Attributes. So that's what you get. So if you want something to have attributes, you do now need to delve into the complex type syntax as opposed to relying only on the simple type syntax. And we'll see examples of that in just a moment. But just to flesh out the additional content models that are possible, you can also declare an element of complex type to have only elements as its children. And we saw this in DTD. You just list them, comma after comma after comma after comma. You can have mixed. We also saw this in DTD where you got PC data, comma element, comma element, comma element, and so forth. Or empty, where at the end of the day, it's got to name the element, and it might have some attributes, but it has no children, textual or element. So what's an example? So here's an example of a complex type with simple content. I've just used ellipses here to just say we don't care so much at this point what is inside this, but here's a canonical definition of an element of some name. It's of complex type, but we explicitly say it has simple content, which just means that, again, to be clear, there's no elements as children, which means what is there, if anything, is going to be textual, and that begs the question, what does that text look like? Well, now we can deploy things like our restrictions, like we had for simple content. It's going to be a string, it's going to be a number, but it's not going to have element content. And similarly, down below, not only can you specify that something restricts a certain base type, you can also extend a certain base type. That is, do more than a data type might normally allow by default, and we'll see an example of that in just a bit. So what about this other content model? So if you want to specify that some element can have only elements as its children, here's an example. And this syntax we did see last time. So if we have an element called student, it's of complex type, which means it has elements as children and or attributes. It's going to be a sequence of name followed by year. Is order important when it comes to the children of student? If you care about validation. In other words, I seem to have written name on one line followed by year. What's the implication of that, if any? Sorry? The sequence. So maybe to spin it this way, is this instance of XML valid according to that schema? Yes. What if I flipped John Harvard in 1636 so that the name element were here and the year element were here? Okay, no. So sequence does imply some ordering, much like DTD did, which we realized got us into some trouble. If, however, you wanted to, let's see, what's the before and after here? Name first, string integer. Okay, this gratuitous additional example. If you have trouble following the notion of a student, here's the notion of a name with first and last fields. I should just cut that slide altogether since it doesn't add anything more. Well, what about mixed content? All right, so mixed content is a bit weird. Here's an example thereof. Mixed content is particularly compelling if you're writing, say, the HTML or XHTML spec, where you do want to intermingle elements and or text. But just to have fun with the example here, in theory, you could imagine, in the spirit of maybe the semantic web, where you have a whole bunch of data, but you have a bunch of subsets of that data semantically tagged so that it's more searchable, so that you can present certain pieces of data differently. So here might be a letter element, and it's mostly PC data, but around some of these pieces of text are some metadata that describe it, which might be useful for a computer. How do you express this? All it takes is saying that the mixed attribute of the complex type element is true, because by default, it's false. So that's all it takes to tolerate within a sequence of these three elements, which must appear in this order, name, order ID, ship date, name, order ID, ship date. To allow PC data to be intermingled, just set that attribute. And that's all, in fact, that it takes. So empty content, fortunately, not all that complex, because really there's not much you need to say. If this is what you want to express a schema for, this instance of XML, which is, of course, an empty element because it has no children, it's opened and closed. This is a foo object, it's of complex type, and it has an attribute. And it's of type string. Is that attribute required, though, fixed, or optional? Optional. So maybe it's not a perfect definition if we really care about bar being there, but it's certainly one way to express exactly that. If I were to try to validate this foo element, foo bar equals baz, is that valid according to that schema? Yes? No?
Yeah.
No one? Nay? Just to pick a fight? So it is valid. But what is potentially misleading is that there's this problem here, but in fact, so long as these things are back to back, that's perfectly okay. Ugly, to be sure, and perhaps atypical these days, but valid nonetheless. What about this? If I change this to just a pair of single quotes around the value. Valid? Invalid? I'm sorry? It's still a string. So is this valid? Sure, that's still valid. Let's take it one step further. No. So now you don't even get to the point of asking the question, is this valid? Because this violates, just to be anal about jargon, what? The notion of well-formedness. And well-formedness is purely syntactical, has nothing to do with the rules underlying what the data must look like. This just means formatting-wise, this document is now broken. Okay, recall that HTML is really quite loose when it comes to that thing. Put them there, put them not there, don't put them there, the quotes marks, it doesn't really care. So model groups is the buzzword to describe the some of the features that we did look at last time, but didn't actually slap this label on it. The label in and of itself, not all that interesting, but does appear certainly in literature or documentation. So how do you express different notions? Well, we've seen sequence, pretty much explains itself at this point. A choice we did see last time as well, which affects conceptually the notion of a loop through a sequence, through a set of choices, and you can pluck one or more out each time based on the min occurs, max occurs values, as we saw last week. And in all, I think I mentioned verbally, but we didn't actually see. If you want foo, bar, and baz to be there as children of something, but you don't care about the order, well, don't use sequence, just say XSD all. And they've all got to be there, but in any order. And that element in particular solved that problem of determinism, recall, 2 weeks prior when we looked at, or 2 lectures prior when we looked at DTD and put that big Ghostbuster symbol with the X through it saying, not possible. Well, with Schema, can you express, I want the data there, but I don't care about the order. Just make sure that it's there. And so that's a nicer way perhaps to express one's data, define one's data so that you're not so anal as to the ordering of it, even though it might all be there. So we've seen this example of a sequence. In English, a name is what in this case? So sequence, name is a sequence of, I'm sorry?
It's a string of any length.
It's a string of any length. Not quite. So a name could be a first element followed by a last element. Or what else could it be? None, right? It could be an empty element because min occurs typically by default is implicitly 1. But if you override that with 0, nothing in that sequence has to be there. And so it's just an empty element is possible with that definition. Now let me add a nickname in here. So just for kicks, it's pretty reasonable that sometimes people have not just one nickname, not just 0 nicknames, but maybe 2 or 3. And if you want to capture those nicknames as effectively a list, and you don't want to get into the list type and having things separated by spaces, but you just want a separate element for each such nickname, well, here we can slap on a trailing element called nick, ultimately of type string. Doesn't have to be there, but can be there as many times as you want, so long as it's after first and last. So this person can now have any number of names. If, though, we're more concerned about choices, we don't really care about everything being there or in a certain order, this example defines a product type as containing what? And we borrowed this from last week, this example, recall. What's a product type in English?
It has child and size and color and attribute effective date. Size and name, it's also there. 0 min occur is 0, that means like there is no size or there is no color.
Okay. Okay, perfect. So just to summarize, product type is 0 or has 0 or more children, each of which can be a size element or a color element. And this is conceptually when we said it induces a loop. So the fact that this is min occurs equals 0, max occurs equals 3, that means that the processor is allowed to loop through this thing 0, 1, 2, or 3 times, each time choosing either of the possibilities, not both, but either of them. And then ultimately you can have a product type being 3 sizes in a row, 3 colors in the row, 1 and 2, 0 and 0, 0 and 1, so long as the math ultimately works out. And the attribute, which is by definition optional, of effective date is ultimately of type date, which is just a standard representation for like a year, month, and date. All right, what about nesting models, just so you've seen it before? Well, almost all of these things, so long as you're reasonable, I think conceptually, can you piece things together? So in this case, a product type is now a sequence of a number of numbers followed by size and color. So again, somewhat arbitrary to be sure, but demonstrates how you can in fact nest different content models. You can absolutely have a choice inside of a sequence or a sequence inside of a choice, so long as everything inside there is well formed and is valid according to Schema's specification. So you can kind of reason through this, a sequence of number elements, exactly one, followed by 0 or more of the things we just talked about. That's all that's added to it.
Say 0 or more, but we have the 3.
Sorry, 0 or, yeah, sphere 0, as many as 3 of the following, just like before. And finally, the all model. So in English, just to repeat what I promised is possible, what is a name in this schema? I'm sorry? Not anything, be a little more precise. It's a first and last name, or it's a last and first name, would be the implication, because each of these things are required, because min occurs, max occurs, and so forth, is true for both, or is rather 1 for both of these, but it doesn't matter what the actual order is. All right, so model groups. So it turns out there is this way to reuse collections of schema elements, and this too can be useful for the sake of reusing code. So if we wanted to use in multiple places the notion of a first name followed by a last name followed by a birthday, and you don't want to define a separate type for that per se, but you want to be able to conceptually copy and paste that particular sequence elsewhere in your schema for whatever reason makes sense in your context, you can define what's known as a group, so that you can reuse in a copy-paste sense or a macro sense something like a sequence or a choice or an all. And you use it as follows. I have here a person defined as a type person info. Well, what's that? A person info is a sequence of a person group, wherever that was defined, followed by country. So in this way, can you extend, in a sense, the notion of what an existing content model is by just tacking on some additional details, but the interesting takeaway is that it is reusable. And you can do this, in fact, for attributes as well. And attributes is perhaps more useful if there's some common set of attributes for your application that you tend to use, like you like your elements to have an ID, an alt tag, ALT, maybe a name and a title, just some basic things that you'd like to be able to trust that every element will have. Well, you can define those in a model group, in an attribute group, and just specify that such elements as person use as their attributes that particular set of attributes. Order in attributes. The important, whether or not I said first name, last name, birthday, or any other permutation? Shouldn't be. So why? How far back in the course can you point for the definitive answer to that question? Well, I know, because I said it, but... So there's no notion of ordering in attributes. And you may have experienced this or felt this when you've played around with XSLT, and the stylus, for instance, just returns all the attributes, but in any old order. When you had your sax parser, the sax parser might have passed you effectively a linked list of attributes, but they may have been in any old order. And even for Project 1, didn't matter what order you plug them in, especially if you're just using a hash map. So who knows how they're being ordered underneath the hood? It's okay. You can just return them in any old order. So here, too, there's no notion, there's no sequence syntax. It just is one attribute after the other, specifying that if they're there, they have to be of type string and or date, such as these. But their use is optional by default. So what about extending? So this was something promised that we'd revisit. So if you have up top there a simple type name size that at the end of the day is a string, and it's going to be a string that's either small, medium, or large. So that we saw earlier, defining a size to be of textual type. But now suppose we have genes. So a genes element, or rather a genes type, has simple content, which just means what kind of children? Just text children. So no element children. It's a very simple model beneath him. It's going to be a simple content, but I'm going to extend the base type called size. So I want genes to have values of small, medium, or large as their text children, but I want to be able to tack on, say, an attribute. And so it's in this sense that you can extend the definition of some base type by adding on, tacking on an attribute, for instance. And in this case, I'm tacking on an attribute called sex, whose possible values are male or female. And there's a lot of nesting and there's a lot of code here, just because it's really very verbose. But at the end of the day, all I'm saying is define a new type called genes that is ultimately of type size. So there's some hierarchy conceptually here, but with the addition of this sex attribute. So it doesn't contradict the definition of simple content. Simple content only speaks to the children of the element. But all complex types can have attributes. So that still satisfies that definition. But recall, each of those content models, to be clear, only discussed children, not attributes. All right, what about extending complex types? So notice, to be clear, size was a simple type here, and I'm just making it complex by adding an attribute. Because again, simple types by nature, by definition, cannot have attributes. Well, what if instead we try to extend a complex type? So now let's steal our notion of product type. Say that it's a sequence of product number type followed by, the sequence of a number followed by a name. Well, what's a number? It's a product number type, which is defined in, I think, our previous context, but that's not so much important for this example. But how do we go about extending this thing? Well, here's a type called shirt type. It's going to have complex content, which means that it's not simple content, which means there's some kind of element content underneath there. That's all it means. What is it going to be? Well, it's going to be ultimately a type product type, but we're going to extend that to have not only product type, but also to have a choice of size and color coming after the product type elements. So think of this as sort of a copy-paste, that a shirt type is a product type that has the addition of the following choices coming after whatever's inside of those as children. But I would say that we're now, with these last couple of examples, pushing, I think, the limits of what is common practice, especially since we're using pretty contrived examples just so that we can fit all of these examples into some context, but just know perhaps ultimately that it's possible, even if not on face value necessarily compelling. Well, what if you want to punt altogether? Well, we saw this last time. If you just kind of want to give up at some point and say, forget it, I don't care what else is in this element, or maybe more reasonably, you just don't care because all you care about is that some data is there, and it's not a problem if more data than you actually need is there, because it's just data you don't support. Well, you can simply specify that after a first name and last name here can be anything, or nothing, but otherwise anything. But how many times can you have an additional third element there? How many anythings can you have after last name? Minimum 0 and maximum of 1. So if we really wanted flexibility, we'd need to add max occurs equals, quote unquote, unbounded, just to really punt. And if we want to really punt further, we can change sequence to the keyword all, and down here as well. Change any to min occurs 0, max occurs equals unbounded. And that means the children of the element called name can be absolutely anything, but somewhere in there must be a first element and a last element. And that's perhaps a nice, if sort of lazy approach of ensuring that the data you do care about is there, but if there's other stuff, not a big deal. Just let it be there. Your application doesn't care. Same deal with attributes. If you want to specify that any old attribute is fine, so that you're not violating the definition of your spec, you can also say, I'll tolerate any one attribute, whatever it is, but also with that use of unbounded, can you say, whatever, let any attributes be there, I'm going to ignore them anyway, it's not going to break my application if they are in fact there. So it turns out that you can offer this, and I chose an example involving 2 different languages just to make a point as to why this might be useful. For instance, in the context when you're integrating with someone else who happens to think of the word of price as cost, whereas you think of cost as price, and really they're the same thing, but you want them to be treated as synonyms, well, you can allow what are called substitutions. So if you've got 2 pieces of XML, a customer and a cliente element, one of whose names is John Smith, the other whose names is Giovanni Smith, well, if we want to tolerate this kind of equivalence conceptually, albeit with different names for these elements, well, we can specify that the element called name is of type string. That's old stuff. But nome, Italian, is in the substitution group for name, which just means make this a synonym for name. That's all we're saying. Tolerate both and treat them as equivalent. And then down here we can also define a customer info. So this is just to define some type that we can refer to, because down here we further specify that a customer is of that type, whatever it is, but cliente is also a synonym for customer. So actually kind of neat. So you don't have to necessarily rewrite your spec if you just want to say that it might be called either of these things, just FYI. So that's actually kind of a useful thing. So I'd say the best summary, and the best summary, honestly, for schema is not to read the 3 separate recommendations in which it was defined, but honestly, this is one of the best websites for this, which is one we keep turning our attention to, all of whose definitions are linked on the W3 Schools site for both all of these elements. Here's some additional elements, and it's a wonderful training resource. So what I'm thinking we'll do, given how sparsely populated we are today and how icy, frankly, it is out, let me talk for a moment about Project 4, specifically web services and where we're going, but then perhaps I'll stick around for quite a while, as long as you'd like, for casual Q&A about the project and the like, because it's not until next week where we'll introduce fundamentally new material that we just haven't covered at all for the problem set, focusing specifically on web services, SOAP and WSDL. But what are these about? Where are we going with this? So web services are a really compelling, I think, use of XML-related technologies. And it doesn't really matter that it's XML under the hood, but web services are all about letting person A execute code on their computer that actually is executed remotely on computer B, but in a transparent way, so that computer A, programmer A, doesn't even need to know where it's being executed. The catch, of course, is that if your network connection breaks or something else goes wrong, all of a sudden you realize it's a remote procedure call, even though you're just calling a local function or method. But the cool thing about web services is that they're intended to be platform independent. So I've used a couple of these things thus far for real purposes. We've used them in the course for Amazon integration, so as part of Project 4, so that you don't feel that we've been having you play in a sandbox the entire semester, and thus it's non-obvious come January what you actually do in the real world. We'll actually have you look at Amazon's API, and for your own e-commerce site, integrate real data and or real prices and or real images and reviews from Amazon using their API. And we'll do this by pulling up a URL that's an XML file called WSDL, which is Web Services Description Language. And it's a fairly arcane syntax, but that's fine because only computers really need to understand it, not humans. But embedded in that file we'll see are the names of methods that Amazon's API supports, the names of parameters and the types thereof, and we'll see references to schema to define what those data types are. And the brilliant thing about web services is that folks have written software that parse that WSDL and generate Java code or C++ code or C# code or PHP code that allows anyone to call Amazon's methods from their own software, but in their choice of language. And the underlying transport mechanism isn't like Java RMI or Corbo or some of these extant technologies, but rather just XML. It's a big old string of XML. SOAP is one such instance. There are other alternatives to that as well. And it is a wonderful way of getting up and running quickly while using someone else's API. PayPal is another one that I've personally used so that we could automate a billing process. PayPal exposes hooks in the form of a WSDL file that we generated some PHP source code for ourselves to use. We type a few function calls on our computer and bam, it gets executed on PayPal services without me having to download their own SDK. Right? So all someone has to do is write a toolkit that can generate the PHP or the C++ dynamically. So it's actually quite neat. And we'll focus on that next week and introduce that to Project 4. So unless there'd be disappointment in heading home early, given the weather and such, why don't we officially adjourn here? But I'll stick around for another hour if you'd like for one-on-one Q&A.